So what we are doing, we do this normally in all box model kind of scenarios. We write again the mass balance in the sediment volume. This is delta x, delta y, delta z is the volume, differential volume of the system. We write rate of accumulation equals rate in minus rate out. Now here I can write other terms if I want to, yeah, I can write many things, same as box model. I can write whatever is happening inside the system. Okay. This is exactly what we did in box model except for two key differences. One is rate of accumulation is now non-zero, it is not steady state, something is not going out in the same manner. Second is that this rate of accumulation term, what is it? So we have to write this in terms of mass by volume. So it is delta x, delta y, delta z into dou Ca by dou T. If I write like this, is this correct? So this has units of L cubed Ma by L cubed into T, m by T. But is this correct, this term? Rate of accumulation as delta x, delta y, delta z into dou Ca by dou T. Is there anything wrong with the way I have written like this? Anybody? Some of you have said no. What will you write in the rate in and rate out? So rate in and rate out is only by diffusion. This is only by diffusion. So which means it is a Na at z minus Na at z plus delta z multiplied by the area, which is in this case x y delta x delta y. So this is the diffusion area is this is going into the system here. Yeah. Nothing wrong. So here this term here is diffusion is minus dCA dou Ca by dou z at z minus of minus dA dou Ca by dou z z plus delta z into x y delta x delta y. There is a problem in this. On the left hand side, the right hand side shows what is going through the in the fluid. The fluid is moving as diffusion, material A is moving in and out of the system in the form of the diffusion which is occurring only in the fluid phase, in this fluid phase. The overall accumulation is happening on the entire system. It is happening both in the fluid as well as the solid phase. That is not solid phase, Ca is only the fluid phase. So therefore we have to add this is a term called CAT. CAT is the CAT into total volume. In this case we are CAT into delta x, delta y, delta z will give you the total mass of A in the volume, which includes mass of A in the pore water plus mass of A on the solids, both of them. Because here adsorption is happening, adsorption and desorption both of them are happening. There is exchange between the liquid and the solid. So the entire mass of what the change here depends on whatever is totally is happening in this phase here. Okay. So now if you divide by delta x, delta y, delta z throughout, and take delta z to 0, limit, we will get dou Ca t by dou z, dou t equals here dA3 into dou square Ca by dou z square. You can work out the these things, we have done this before. So this minus this, it becomes essentially, it becomes this term will become delta z, and that delta z goes to 0. This is the definition of a derivative. This minus this is the dA by.
Sir, we are considering only in z direction.
Yeah.
Won't there be?
Now here we are, our main, you can do all the 3 directions. In this model we are doing z because that is the primary driving force there. It is already always going in every direction, so that is already there. So this is to just look at our description of the interface at the sediment water interface, that is at z equals 0 in the z direction. Now there is also transport going on all the time during this here. So you can write the general 3-dimensional mass balance for the system, that is always there, which means you have to define boundary conditions and all that. Yeah. So this, as I mentioned, this is a synthetic problem, because we have to start somewhere. We are starting like this. If you want to track the entire history of this contamination, it is still going out, still spreading. It can continue to spread outwards, but we will see why. We are not interested at that for the time being because of some of the things we will do here now. Now this term here, dou Cat by dou t, so this is the definition of the derivative, this is the definition of derivative here, this term here. You will get this, you can check it out yourself. So here in this thing there is this term called dA3, which I have written as dA3, which is diffusion in porous medium. This is different from dA2. So there is water here, diffusion is actually happening in the pore water. So but dA3 is the term that we have written here. So dA3 is usually defined as dA3 equals dA2 multiplied by a function of the porosity of the system. This is because normally when you compare, when you look at diffusion in a fluid, yeah, if you have pores, so if you have a same driving force between 2 systems of diffusion, we look at the case of dA3. I am going to go ahead into the next slide. Everybody finished with this slide? You need? So this the term dA2, the diffusion is reduced because now for 2 reasons. One is, let us say there is diffusion is happening like this from here to here in an empty channel. Yeah. Now there is another case where this channel is now filled with some solid. If the same concentration gradient exists, say let us say we have Ca1 and so rho A1 and rho A2. So we will call it rho A1 and rho A2 subscript, superscript, without using the subscript. At this point and this point. So let's be more simpler, clearer. We have rho A2 at Z1 and rho A2 at Z2, 2 things. So there is a concentration gradient between these 2, and the same concentration gradient exists here also. But here material can move, diffuse nicely throughout through this. Here it cannot move, it can only move in these gaps. So already it is reduced. That is one. Second, if it goes here, it will turn, it has to diffuse in this direction, it has to go like this. It takes longer for it to go, less of it can go, first that is the problem. Second thing is it takes longer for even that less, because it is not a straight path, it is a tortuous path. So this function here therefore reduces the diffusion, effective diffusion of a material across a porous medium. Okay, this is a simple explanation. This is called as effective diffusivity in a porous media, and this is a function of the porosity. So There are different equations for that. dA3, the very commonly used expression is dA3 is dA2 multiplied by epsilon 2 raised to 4 by 3. This is called as Millington-Quirk's expression, very old equation. But there are other equations, people dispute this equation and they do not like this equation because it makes some assumptions and it looks too simple. Processes inside porous material is very complicated, especially if the solid has internal porosity and all that. So, here we are not assuming all that, nothing. The internal porosity means there is pores inside the solid here, and the diffusion is not a straightforward process. It can go in, it will take a long time for equilibrium to achieve, all those things are there. So, this is all adsorption and desorption is very complicated in these systems. So, we simplify it so that we can model it reasonably easily, and we use that as a starting point. Okay. So, general expression for dA3 in the Millington-Quirk's expression is dA3 is dA2 multiplied by rho 2 raised to 10 by 3 divided by which means that there is another phase in the pore space which is not for example, if you take the case of soil, if you have unsaturated soil, some part of the pore space is filled with water and some of it is filled with air. So, this assumes that epsilon T is equal to epsilon 1 plus epsilon 2. Some part of it is filled with air, some part of it is filled with water. In this case, this happens, then you have to use this expression, but this expression reduces to this expression when epsilon T equals epsilon 2 or epsilon 1, it becomes rho a to epsilon 2 10 by 3 divided by epsilon 2 square. So, this becomes 4 by 3, 10 by 3 minus 2 is 4 by 3. Okay. So, this is a general expression for this thing. So, the general expression in the Millington-Quirk's this thing is epsilon diffusion coefficient dA3 is dA2 into epsilon 2 10 by 3 divided by epsilon total, and the same as this is dA3 sorry, we will call it as dA3 2 because it is still in the water. We can also have dA3 3 1 because we have dA1 epsilon 1 10 by 3 divided by epsilon T square. Yeah. There are other equations. So, if you go and look in the literature, search for diffusion coefficients as a function of porosity, there are other equations as well. So, the people have devised other, this is a very old code. If you do not have any other equation for your system, you can use this as a starting point. This will reduce the, so we now go back to our equation. We now have dou CAT by dou T equals dA3 into dou square Ca by dou Z square. This is the equation we have. Okay. Now, we have two this is a partial differential equation with two dependent variables CAT and Ca. Okay. Sorry, not CAT, rho A2. So, concentration in the so, now we need some relationship from here. So, three possibilities, there are several possibilities, one of them is the following. So, rho AT into the volume, total volume, we have said that is mass of chemical in the liquid. So, what is that? Mass of chemical in liquid is volume of 2 times rho A2 plus mass of chemical in the solid. So, in this given volume, this is delta x, delta y, delta z, this volume is divided into two phases here. So, if I write down rho AT equals V2 by Vt into rho A2 plus M3 by Vt into WA3. This is epsilon 2 rho A2 plus, what is this term? Rho 3 2. This is the porosity, this is the porosity, this term is what we call as bulk density. We have seen this in our first section. This is a representation of the porosity of the solid. bulk density. So, bulk density is very high, which means that the porosity of the liquid is low, the solid fraction is higher. The bulk density is a representation of the solid fraction. It is a mass by total volume. Okay. Now, we have this equation. Now, we have rho AT equals epsilon 2 rho A2 plus rho 32 WA3. Now, we have somewhat split it up, but now we still have two numbers here, this one and this one, and we can't put it into the differential equation and solve it unless we have one more equation that connects rho AT to WA3. So, there are various options for this. Okay. So, we need one more equation that connects WA3 and rho A2 in the porous system. So, the first assumption we make is case 1 is we will invoke what is called as a local equilibrium assumption. These are all simplifications for what could be the real scenario, what is happening in the system. The local equilibrium assumption assumes that when a solid is in the near a fluid, there are these chemicals that are sitting here, we have, and there is chemical here. The rate at which the diffusion is occurring is almost the same order of magnitude at which this absorption is happening. So, what it assumes that at every point it is here, it equilibrates very quickly. This exchange between the solid and the liquid, the fluid, pore water is very quick. So, which means this here is diffusion, here also can be diffusion. The mass transfer coefficient associated with the adsorption is also diffusion based, there is no flow anywhere, there is no water flowing anywhere. So, everything is diffusion. So, therefore, this scale of this one is equivalent to the rate at which this is happening. So, it is a fair assumption that this is all at equilibrium quickly, it comes here and not quickly, but it is at the same rate. Material will not go from here to here before it comes, it has a chance to come to equilibrium. So, let us say I have a velocity here, its flow is happening, definitely a velocity is much higher than the diffusion, because adsorption and desorption take place by diffusion only. And therefore, if that is happening, then we can't have local equilibrium assumption, we definitely have to have some other equation to describe the concentration on the solid surface with reference to the concentration in the pore water. But right now I can assume, if local equilibrium assumption, I can assume equilibrium at every point, because the process is so slow, the rate of diffusion in pore water is of the same order of magnitude as the rate of adsorption or desorption. What does this mean? This means that WA3 and rho A2 are now connected using the partition constant. This implies this. So, if we are using a linear isotherm, we use this. Most of the environmental cases, this is enough. This will be sufficient. So, we take this now, this equation, and put it back into this. So, now our rho AT becomes epsilon rho A2 plus rho 32 into rho A2 into K 32 star. Now, we take out rho A2 here, it becomes epsilon 2 plus rho 32 into K 32 star. This equation, now we put it back into this, we have dou by dou T into rho A2 into epsilon 2 plus rho 32 K 32 star equals dA3 into dou square rho A2 by dou Z square. This now becomes, you pull out all of this. So, this all of these things, this epsilon 2 is porosity, then there is bulk density and the partition constant. These are not functions of time. If you believe they are not functions of time in the system, yeah, when can it be a function of time? They are not a function of time means they are not changing within the process at all. Then the only way they can change is if something is happening. The bulk density can only change if I add more solids into the system or if I remove water from the system and the thing shrinks. It is a very fair assumption that this will not happen in the time scales that you are looking at. Sediments will compress, that happens, but that happens over very long time scales, much longer than if you look at porosity distribution in sediments, there is a change. Very deep below you will find very highly compressed sediment, and as you come closer to the surface porosity is slightly larger. But that is now porosity is a function of space, but not a function of time. So if it is a function of space, then you have to we have to worry about something else. But for the time being we will assume it is not a function of anything, it is constant in space and time. So we will pull it out. So when it comes out of the derivative, okay. Now this term becomes, you can write it now as dou rho A2 by dou T equals dA3 divided by epsilon 2 plus rho 32 Ka2 32 into dou square by dou z square. This is now the differential equation that we can solve. Now if you look at this differential equation, this term here, if I compare this with this term, the normal simple diffusion equation is, the simple diffusion equation is dou rho A2 by dou T equals dA2 d square rho A2 by dou z square, normal diffusion equation. If my diffusion is occurring in a simple tube, the equation will be dou rho A2 by dou T equals dA2 into dou square rho A2 by dou z square. This is simple diffusion equation. If you compare this diffusion equation to this equation, several things are different. One is dA3 is there, so it is effective diffusion coefficient. This term, this entire term, if you look at the magnitude of this term, is very much smaller than this term here, for two reasons. One is dA3 is there. The second reason is in the denominator, if you see, there is these two terms here, rho 32 and Ka32. Okay. This represent the value of Ka32, partition constant. What does it mean? If the chemical is highly adsorbing, the Ka32 number is very big, very large. So if the Ka32 is large, it reduces the magnitude of diffusion, it retards the diffusion. Okay. And if you also have a large number of solids, it will retard this further. Okay. If you have a very highly adsorbing solid, but a lot of it is not there, very small amount is there, which means bulk density is small, then the total magnitude of adsorption removal is small. But if you have a very highly adsorbing solid and a lot of it, this denominator becomes big, very big, which means the magnitude of diffusion, the rate of diffusion now is slowed down. So if material is trying to diffuse from here to here, it is not happening fast, it is happening very slowly, because it has to now interact with the solid. So this is retardation. The solid acts as a barrier because it is adsorbing and desorbing. So material is coming away from here, but it is also not allowing material to diffuse straight through, it is intercepting it. So this term in the denominator is known as a retardation factor. So we write this equation as dou rho A2 by dou T equals dA3 divided by RA32, where A32 is called as a retardation factor, is equal to epsilon 2 plus rho 32. So now we have to solve this equation. If you solve, you will get rho A2 as a function of z and time. Okay. We will see this tomorrow morning, how to solve it different. To solve it you need boundary conditions and initial conditions. You need two boundary conditions and one initial condition. So we will look at what are these and how can we solve this equation, the variations of this equation in different scenarios, and then the application of this in a soil air system. So, we will see that tomorrow.